detection engineering dispatch. This is about identifying files, identifying encoding, doing decoding, potentially identifying encryption and doing encryption and decryption of data. This is just to get you started if you're not familiar with the topic. I've noticed a lot of analysts that are even really good with log stuff don't necessarily have this knowledge, so I figure it's worth doing a session on. So basically, this will allow you to identify file types using CyberChef. It'll teach you a little bit about encoding and encryption and how you can identify them on a result just by looking at it, or at least get hints about it. It should allow you to identify single and multi-byte XORs and what that is, where it's used. And I'm also going to go over RC4 encryption, and we will encrypt and decrypt a piece of data with it and show you how it looks. So this is useful for any analyst that has to look at PCAPs, for example, because files go over the network all the time, they get detected, and you have to rip them out of PCAPs and look at stuff. And the context of how that file got over the network might not necessarily be complete, so you might have to do a little digging on files to figure out what they do. So there's also, you can just acquire files from machines. We tell our customers to do that all the time. And in instances where we see something suspicious and they have to get more insight from a file. And it's also very useful for like CTF challenges. And it's just fundamental knowledge that is very useful. So, oops, that was supposed to be before. So anyway, CyberChef, here's the link for it, .github.io/CyberChef. Go there, and that's where we're going to use, that's the tool we're going to use for this. It's very useful for all types of stuff an analyst needs to do. Analyzing files, encoding files, encrypting files, decrypting, calculating entropy, a whole bunch of different stuff. And I'm going to show you a whole bunch of different things or features that are part of CyberChef, including XOR base 64, the 2-hex stump, RC4, entropy, and magic commands. So encoding is basically a way of changing a way data is represented. The reason why you encode stuff differs, but that's basically what it does. They can often be reversed just by looking at them, so they're not particularly good for security or hiding data, but sometimes bad guys do use these to hide stuff for whatever reason. And it's also used just for regular applications as well. Base 64 is extremely useful for the web, and there's other encoding methods that are useful for cyber and other things that we'll talk about. The ones we're going to go over in this presentation are base 64, hex, and decimal, but there's many, many, many others. The first encoding we're going to go over here is base 64. Most of you recognize it. And we're going to take what is in a file for the challenge and use it for this presentation. So Jeanette should be able to give you a link. Did you share the link yet?
Yep, link is in chat.
Okay, so what I want you to do is put that on your clipboard, go to CyberChef here, just start over, and then I want you to paste it into this input here. So just quickly, what this does is there's an input and output. Recipe is where you can drag stuff that you want to do in sequence. Since a piece of data might be encoded or encrypted multiple times, you might need to use multiple steps to format it as well. But we took our input that you should have from Jeanette, and I just chucked it in here. And the first thing we're going to want to do is use from base 64, because that's what this is. Now, if you notice here, there's an equals sign at the end. That's padding. It's a way to identify base 64 just by looking at it. It can have up to 2 equal signs or none, depending on the length of the input. In this case, it has a length of 1. I want to show you something really quick as well before we get started on this, but actually, we'll just keep going here. I'll show you that later. I lost it off my clipboard here. Chuck this back in. Okay, and then I use from base 64. What you notice here is that basically the result has strings in it. You could see stuff challenge.mp3 in here. You can see we'll go over this, but this is the magic byte PK. And if you keep looking through, there is more strings. Solution is in here. What this is basically a zip file. And the way you can tell that it's a zip file is because of the PK. But I think I'm getting ahead of myself here a little bit. All we really needed to do was take it in there and paste it. But what we just did is we transported some data using base 64. We took it from one place, pasted it in another, and the result is in binary format, which is really useful. Or it's useful to transport it in binary format, because if we just copy and pasted this gibberish here and send it over an email, it probably would get mangled by the time it got to our destination. But Base64 did really well in preserving what we had. So it's good you can use it to transfer data between OSs, and it preserves it exactly the way it was. So next, I got into it a little bit, but the magic bytes are the first few bytes of the file that serve as identification. The file extension doesn't always matter in every single context. Like, for example, if an attacker sets up shellcode or something, or malware that loads a file with the wrong extension, it's not really going to matter that the extension's wrong, because the program knows how to process it, or the OS component knows how to process it. So oftentimes the extension won't make any sense. Like, there could be, a file with a .mp3 extension that's actually an executable. Happens. I've seen that before. Some cases it does matter. It's a way for the OS to recognize what application to potentially open it with, but there's no rule saying that it needs to match all the time. And sometimes attackers change extensions as well. And you don't always need an extension either. Files can have no extensions. In that case, you would have to open it and look at it, or acquire it and look at it. So to see the actual byte sequence that comprises the magic byte here, we need to use this other command, hexdump, to hexdump. And what this does is it has multiple rows here. So in the first row, we have the offset, which is how far into the text we're looking. So this is 10, 20, 30, all the way through. The next is a ASCII representation of the hex that makes up the file. So if there is a null byte, for example, meaning a byte that's just 0, 0, it will print here just a period instead of a null byte, because you can't see a null byte, and this is designed for humans to read. You'll notice that in the zip file, there's like I said, there's patterns. There's a lot of null sequences here, which can be useful later. And what I want to do is go back to our presentation here. We want to look at for this, we're looking at these PK. What magic byte is this PK? 54B. So if we go to Google, this. Okay, 54B is zip file format. These magic byte sequences are documented. In this case, it's just documented on Wikipedia, but it's documented in a bunch of different places. Like, this is something you'll see often. So as a shorthand, when I look at files like this, I know that basically this means it's a zip file. So basically what I want to do with this now that we know it's a zip, I want to use the save output to file and save it to something on my machine. Hold on. What's wrong with this? What did I do wrong here? It looks like it might have been copied a bunch of times, which might be the issue. Just a second here. Oh, I know what I did wrong. So I was saving the hex dump. What I meant to do is save it as a zip file. And this is going to be really common when you're looking at this stuff. You're going to wind up messing up once in a while, and it takes a lot of different steps. That's normal. Okay, so this time when I saved it and I double click, it did this. It created a folder. I'll show you one more time. So if I double click it, it basically unzipped it and created this folder, which is what we wanted. So now we have 3 files. Okay. So we have a challenge.mp3 file, which is going to be the challenge part of this. We're going to have the presentation, which is what we're going to go over now, and the solution, which is the answer to the challenges. Let's go into the presentation here. And what we have is basically, it looks like this. It's just a bunch of numbers with zeros on the end. So I'm going to take this. Let's go back into CyberChef. I copied it to my clipboard as well, by the way. And I'm going to chuck it into here. And I'm going to use this from decimal, drag it into the middle. So what this did is these are encoded in decimal. So you know how bytes can be from 0 to 255 in value? All this does is for each byte, it has a number. So for null bytes, it's 0. That's why you see all these zeros in here. So let's do from decimal. And now we have a different magic byte sequence. We have MZ, which is probably the most famous byte sequence. It's for PE files. And I bet you if I look in here, 4D5A. So if I use to hexdump and we look here at the representation of what this is, the hex representation, It's 4D5A. So that's the magic byte for this. And that's a DOS Z executable or an MZ header. This isn't a full file. It's also known as a PE file as well, portable executable. So this file could have had a .exe extension, except it would have been much longer. I didn't include the whole file because we don't really need it for this to show you what I'm trying to show you. But basically, it's going to be useful for this, and it's going to show you how you can recognize encoding and stuff like that. But you will open files in the future and notice this MZ header. An executable doesn't need to only be a .exe. It can be a .dll, which is also a PE file. It can be like a .pif file or a .scr, a screensaver. Those are also portable executables. And it can even have a non-executable extension. It can have no extension, and if you point cmd.exe at it and try to run it, it will run. So that's kind of what I was mentioning before in the presentation about the extension doesn't always matter. Okay, any questions so far? All right. So now we're going to get into the fun stuff. We're going to do our first encoding method that's not something you probably already know, XOR encoding, or you may know XOR encoding. But this is a very simple encoding method. It's a bitwise encoding method, meaning that it does something to each byte, and it has to do, we're not going to go over exactly how it works because I would probably bore you to death, and there's ways of spotting it in the wild that are easier. They're visual. They're not mathematical, that I'll show you. XOR encoding is always going to involve a key, and the key could be 1 byte. And if it is, that creates different properties than a multi-byte, which is like if I wanted to use my name, that's a multi-byte key. So the way you can spot XOR encryption, or encoding rather, is usually repetition, and I'll show you how that looks in hex. It doesn't change entropy. We haven't covered entropy too much yet, but I'm going to get into that. Whether it's single or multi-byte, and it doesn't actually securely hide data, even though it might look at it like it at first. So let's go to entropy quick next. Entropy is the randomness of a given input, and the higher the entropy, the more random it is. So if we go back to XOR here, let's start with a single byte XOR. Let's say we wanted to encode this. Let's say we're an attacker, we're lazy, and we want to hide it, and we want to use a key of AA. And now, actually, let's use the letter K in UTF-8. Okay, so do you see what that did right away? What that did right away is now there's a ton of Ks in there. And the reason for that is, if I take out the K, if I take out the XOR, the reason for that is because all of the null bytes in this file were XORed. The XOR of a null byte with any other byte, the result is always going to be the other byte. So you'll see if I XOR with K, the null byte should turn to K. So if I go back and put in XOR and T is UTF-8 and I put K, all of these change to K. Now, let's say I wanted to make it a little harder and I wanted to use a multi-byte key and I want to use my name. Now, it's a little harder because remember, not every single byte in there was null. So there's stuff that we don't, when we're looking at it as the result, we're not going to actually know what was underneath. But if I put in my name again, we have some parts of it. Here was some other character other than a null byte. That's why it's messed up. And here there was some table looking stuff. So that got messed up. But I purposely added a ton of null bytes at the end to demonstrate this. You see how it's just repeating my name over and over and over again? That's because there's a huge number of null bytes at the end of this file. Now, you're not always going to have that luxury, unfortunately, but in this case you do. And whenever an attacker decides to use XOR for a PE file or a file with a ton of null bytes in it, this technique would work. Now, let's say they encode a file that's not a PE file. Let's say it's just a news article. In that case, it's going to look a little different. It's going to have space. It's going to have a lot of spaces, probably no null byte. And you'll notice that, for example, if I XOR with my key of K, the result will not be the same because a space is different value than null bytes. It's 20 and the null is 0. So it doesn't work for everything, but if you know a little bit about what's underneath the text and somebody uses an XOR, you can figure out stuff about it and potentially figure out the key. So based on what I showed you, like even if you have a really long key, it's not going to take that much time for somebody, if they know what they're looking for, to figure this out. And unless the data under it is so unpredictable that you wouldn't be able to guess, and there's no hints around as to how it would be used, which is almost never happens. There's usually hints as to how an encrypted piece of data will be used. And you need to use those hints to figure out what's inside it sometimes. So any questions on XOR? That's a very common encoding, and it garbles the output, but it doesn't really hide much. What does hide stuff, though, is encryption. Basically, encryption is just taking an input, running it through a well-designed cryptographic method, and the output is ciphertext, which is basically almost completely random data that doesn't let you figure out the encryption method. So you know how I can tell if something was XORed by seeing the repeating patterns? For all well-designed crypto algorithms, you shouldn't be able to figure out the algorithm based on the output, because a well-designed crypto algorithm should output almost completely random data, and its strength can be measured by the randomness of the data that it outputs, because the less random it gets, the more insight an analyst looking at it has. So encryption will have high entropy. What I didn't show you before that I should have, let's use the entropy feature. And I'm looking at the entropy of my decoded file, 1.48. That's very low. So it's suggesting that the data is not very random. It has a pattern to it. And if we go back and we look, there is a pattern to it. The pattern is that there's a ton of null bytes, and there's this text. This text also has a pattern. It's all ASCII. That's different than this, which is not. It's all binary. That matters for entropy. Binary data is usually higher entropy than just ASCII text, just because there's a wider range of numbers that can be used. Okay, so let's go back. Let's do entropy. So we had an entropy of 2.4. Now let's XOR it again with a single byte key of K. The entropy doesn't change. The reason for that is because while it masks the data, so if I go back here, and I do hex dump to hex dump, it does change how the data look, but oops, this shouldn't be here. I was wondering why that looks so strange. That still doesn't look right. I'm guessing that looks right. Okay. So where was I? So we masked the data, but the randomness of the data did not change. Only how it looks and only how it's represented. So the entropy didn't change. The entropy is still low, suggesting that it's not encrypted, and it's not. So even if I use a multi-byte key, let's see what the encoding is. What the entropy is. It's a little higher, but not much higher. And a big reason why it shot up is because there's so many null bytes. There's so much of a pattern to the initial one. The bigger the file gets and the less random the less non-random the file gets, the less the XOR multi-byte is going to matter, but it changes it a little bit. So now let's go into RC4 encryption. So RC4 is probably one of the most common encryption methods seen in malware. It's just a nice algorithm. Can use it on multiple platforms and OSs and stuff like that. Look at data, transport data as well. So it's favored by a lot of attackers, but there's other encryption methods out there that are useful. AES and DES I've seen as well out in the wild. RC4 is a symmetric encryption algorithm, which means the same key is used to encrypt and decrypt. And that's different than asymmetric, which has a key pair. And symmetric encryption is used for things like malware C2 communication is commonly RC4 encrypted. Whereas with asymmetric, like some of the way information is encrypted when it's transferred over HTTP and stuff like that, HTTPS rather, that will use asymmetric. But we're just going to use RC4 for this. That's the only crypto algorithm we're going to use for this. And the reason for that is crypto algorithms are really not that interesting from the perspective we're looking at it as an analyst, because if it's done right, it means that basically the output of it should be almost random. So we need to know the algorithm, we need to know the key, In some cases, you need to know an IV value. You don't for this. But for some of the other ones like DES and AES, they have other parameters. So if you know that something is RC4 encrypted and you have the key, you should be able to decrypt it. Some developers and certain threat groups, they prefer certain crypto algorithms. So sometimes it can give away who might be doing an attack, but that's something like cyber intel analysts look at. And you would see the algorithm used embedded in the malware, not necessarily in whatever outputs it gave, because it's supposed to be hiding data. Okay, so let's go back. Let's try RC4, and let's compare it to the XOR we did. So we're going to use RC4. I'm going to use a key of my name, and let's do hexdump. Okay, so you should notice a big difference. Well, the first one had patterns, and we know it's in this area. We know it's in this area of the file. It's all null byte. But look at how random it is. It's almost completely random, like it's supposed to be. That's what a good crypto algorithm output looks like. You can almost see like if you scroll through it, you can almost see like there's no pattern to it. It's completely random. Now, what we want to do with this is let's check the entropy of this. Now, remember before we used XOR, the entropy wasn't changed that much. It was changed a little bit by the multi-byte, and it was unchanged by the single byte. But let's see what it is for this. It should be way higher because the data is random. It's 7.9, which is very, very, very high. If we look at all this stuff, it says 0 represents no randomness. For a paragraph, it should be 3.5 to 5. Compressed data is usually over 7.5, and encrypted data is usually over 7.5. We encrypted this with RC4, and it's over 5. Now, notice that if I change the key, by the way, here's a visualization of it. It's like all the way to here. And if I take off the RC4, it's all the way to here. So there's a visual way of seeing it. So it did fall in the encrypted and compressed range. Okay, now let's go back. Oh, I want to show you one more cool thing about entropy that I forgot before. Let's just look at, if we put in just AAA multiple times, the same thing, the entropy is 0. But as soon as I introduce B, it goes up, and then C, D, E, F, G, H, I. See, so the more, that's just a way of it getting more unpredictable, and the entropy goes up. Okay, keep going here. I'm quickly going to go over compression and hashing. They're kind of like encoding and encryption, but they aren't. Compression obviously shrinks the total output size. But what that effect does is basically it makes it have a higher entropy because it crunches a larger piece of data into a smaller piece. In order to do that, they have to like manipulate individual bits and stuff like that. And the result of that is it just looks more random, and it raises the entropy. Like if I had a file of just A's that had an entropy of 0, and then I went and then I compressed it, the entropy would be much higher. Hashing is good for comparing results, and that's basically all it's used for. It's great for looking up files, and we're going to use hashing to see if the answer you get from the challenge is right. But I'm not going to say, I don't say in the solution what the answer is. I just give you the hash of the answer. So what you have to do is figure out what the answer is, compute the MD5 hash of it using CyberChef, and then compare the results. If they match, then you know you have the right answer. So that's just an example of how hashing is useful. It's obviously also useful to look up files on VT and stuff like that when you hash an executable file. Okay, so something I want to show you really cool about XORed data that might interest you is, let's go back and do from decimal. And let's do an XOR key here. And we're going to do a multi-byte key. We're going to do a key of tasing my initials. Now, let's assume we didn't have, let's say it was cut off here or something. So take out all the zeros of it and go to here. And let's say we only had it up to here. But for whatever reason, we knew that this was the start of a file and the start of a PE file. Let's say there was some malware that said, take whatever you get and whatever the piece of data you get is, decode it somehow and execute it. You may have a scenario where you know all these things, but you do not know the decoded result of what's being fed in, or the decrypted result, or I'm sorry, decoded result of what's being fed in. But let's say we assume it's a PE file, but we don't know what the key is. Take all these out. Well, we know the first 2 bytes should be Z, 4D5A. Let's XOR again. So we know the first 2 bytes were MZ. Let's do MZ again. Now notice, when I XOR the first 2 bytes with what I know them to be, MZ, I get the key back. That's how it's supposed to work. I've used this method before many, many times to figure out a couple pieces of information that's very useful. If there's a long multi-byte key, like sometimes attackers will use XOR keys that don't represent any real text. They're just like randomly generated. In that instance, it would tell me a couple things about the key. It would tell me where it starts, which is very critical. For a multi-byte key. It's a critical piece of information because it'll tell you how to align the data you're trying to decode. And it will also give away part of the key. Since my key was only 2 bytes, I have the whole thing. But let's say if this key was, 50 bytes, it would be very useful to know at least where it started and the first 2 bytes of the key. I would still have work to do to figure out what the rest of the 49 or the 48 bytes were. But we would have that. So that's useful. One last thing I wanted to show you real quick is the magic feature of CyberChef. This can be used for the challenge, and it could be used for all sorts of stuff, but it's a very useful part of CyberChef that tries to decode stuff without knowing anything about it. So let's say I have my name, and then let's say I base 64 encode it, and then I use, decimal. Let's see if I can use this magic feature here to figure it out. Okay, it did figure it out. What this does is it has a list of encoding features, and it kind of just brute forces all of them and gives you a result. The most plausible are at the top, and it uses entropy to figure out what the most structured answers are. My name is the most structured answer, which makes sense. That will help you in the field, and it will also help you for the challenge. But if you want to challenge yourself a little bit more, try not to use magic and see if you can get the answer. But magic is great. If you're stuck, try it and see what happens. The worst thing that can happen is it tries a bunch of stuff and none of the answers make sense, in which case then it's encrypted or it's encoded in a way that magic can't help you figure out. Okay, so that's basically what I wanted to show. Any questions, by the way? All right. That's basically what I wanted to show you, but let me show you the challenge stuff. Sorry, I'm dragging some stuff out of the way here. There was other stuff in the file you decoded and wrote to your machine. There should be a file named challenge.mp3 here. You can probably just load it in here. You can open files with this. By the way, don't open malware on a Windows machine using CyberChef. It should be fine, but I would recommend doing all of your analyst stuff on a Mac just in case. But let me load challenge.mp3. This is not malware. It's totally fine to load in here. That might have given a clue. But what you want to do is take that, load it into CyberChef, and then try to decode it. Try not to use magic. Try to decode it using stuff I showed you in here first. And you're going to have to think a little bit out of the box at the end. There's something that is kind of like detective work that should be kind of obvious at the end that you'll have to think out of the box for. But everything else I should have mentioned in this presentation, the answer is an 8-letter lowercase string. You take that string and then you use MD5 in here to, let's say it's Kevin. Use MD5. You compare that to the hash that's in the solution here, and if they match, you got the answer correctly. But don't open solution until you're ready for the answer. Okay, and there's at least one red herring in the challenge that I mentioned in this presentation of something that attackers do. And it's towards the beginning, and it's meant to trip you up. That's pretty much it. Hope you find this information useful. Play around in CyberChef. Try different encoding methods. Like if you want to learn about like DEF, see this would involve a little bit more. When I mentioned there are other parameters, you need to have an IV value. You have to have a mode. But it's something to play with. It's not as commonly used as RC4, but it's out there. And there's also AES, which should be similar. And if we ever release some kind of CTF thing, this type of stuff will definitely be what's going to be the first steps. And if you do a CTF somewhere else, these are also probably going to be some of the first steps. That's pretty much it. I'll hand it back over here.
Awesome. Thanks, Kevin. I guess we kind of have to release a CTF next year now.
Well, Mac mentioned it to me, so.
I mean, whoever's on this call, you heard it first, so it's probably gonna come in 2024. But hey, just wanted to again thank everybody that's joined today. We'll of course I shared the link in the chat here, but I'll follow up with you guys in email, send you guys a little something as a thank you for being a part of our detection dispatch community this year. It is our last one, so we'll be back swinging in January. We'll keep you guys updated on when that first episode comes out in January. We hope you enjoyed today's. I'll also be send over the on-demand episode of this if you want to like rewatch or do the challenge again or share it with somebody at your company or a colleague or something. But if there are no more questions, any closing thoughts from Kevin or anything? You have anything, Kevin, for us?
No, I just hope that was useful. I'm sure it will be. One day you'll open a file and you'll be like, where have I seen this before?
Awesome. Well, hey, thanks everybody for joining. Have a great rest of your week. Thank you.
Yep.